Hi, my name is Joshua Rego, and I'll be presenting some preliminary work done with Dr. Suren Jayasuriya on robust lensless image reconstruction via PSF estimation. Several computer vision applications can benefit from additional information from images while keeping camera cost and size low. Tiny robotics, for example, can greatly benefit from smaller, low-cost cameras. These are some examples of projects from multiple institutes. As robots get smaller, lens-based cameras become less feasible to use. Lensless cameras can be a promising option. Getting rid of the lens allows for a near flat form factor as the mask can be placed much closer to the sensor. It also allows for lower cost and complexity in construction with fewer parts to configure and account for. This is an example of the lensless camera developed by Hitachi, showing a much smaller footprint without a lens. Additional applications include 3D microscopy, depth estimation, and also privacy preservation, since the captured image usually can't be perceptualized by us before reconstruction. The problem with traditional reconstruction methods is that they still need some known information from the camera model. This may be in the form of a point spread function or a coded mask, but these may not always be available, and there also might be variations in the calibration image. Traditional reconstruction is also a very slow process that requires several iterations to reconstruct adequately, and the reconstruction quality might still not be up to par with lens-based cameras. There's a lot of research in the field already. Some prominent traditional methods include flat cam that implements a coated mask with transparent and opaque features that diffract light to cause unique mask shadows on the sensor. Diffuser cam utilizes a diffusion layer as the mask that scatters light from the scene onto the sensor. There are some deep learning approaches that have also been used. The one to the top right uses the flat cam model and implements adversarial training to improve reconstruction quality, while the bottom right uses the diffuser cam model and utilizes a modified ADMM and UNet architecture to improve quality. So we know that utilizing deep learning for image reconstruction can provide a drastic improvement on reconstruction quality. Some limitations of prior research: while traditional methods still require prior information from the camera model, data-driven methods tend to learn the mapping for a single PSF. This doesn't generalize very well to variations in the PSF and may require additional training for each new camera. The goals for our project are to utilize adversarial learning to show that high reconstruction quality can be achieved without the need for a calibration PSF. Additionally, incorporating a network to estimate the PSF and contribute to the image reconstruction should help better generalize for PSF variations. The approach that we use is to take the input image and feed it into two separate generators, one for the image reconstruction and the other for PSF estimation. Both outputs also have their own discriminators to determine how realistic the reconstructions are and are trained using the Wasserstein distance. We then feed both these images to a forward convolution model to generate an estimated lensless image again. Both generators train on their own MSE and adversarial losses, as well as a common MSE loss for the estimated lensless output, as they both contribute to this. The image generator also trains on the perceptual loss using a pre-trained BGG16 network, and all contributing losses are weighted by the corresponding lambda values we determine. These are some early results for the PSF estimation network. The first column to the left is the original PSF in the dataset. The rest are randomized PSFs used to create synthetic lensless images. We see that the network has an easier time reconstructing for the original image as the network was pre-trained for this, but has some trouble with the randomized synthetic data so far. Additionally, it seems that the network is averaging for a common PSF estimation rather than accurately estimating individual PSFs. This may help with generalization, but will result in a loss of reconstruction quality. These are some preliminary reconstruction results. While the generator can still reconstruct fairly well from the pre-trained parameters, we see a noticeable drop in reconstruction quality, primarily on finer details as seen in the image of buildings. This isn't up to par with the state of the art at the moment, but we hope to get closer while still staying robust to variations in the PSF. In addition to the diffuser cam and synthetic datasets we've used, we plan to capture an additional high-resolution video dataset using multiple PSFs. These are some images of the mirrorless camera and diffusion mask mount that we're using. Currently, the models are trained using 480p datasets. We plan to expand this to high-resolution reconstruction, potentially using a progressive GAN approach to improve training results. Additionally, image reconstruction can also be transferred to video-based reconstruction, while comparing methods for single frame versus series of frames to find a good approach. Thank you all for watching.